All right, get ready for this. We're going deep on grid LSTMs today. Now, you might be thinking, another neural network, so what? But hold on. This one's different, I promise. It's like, imagine, trying to analyze like stock market trends or maybe predict protein folding. These are things where remembering information from like way back in a sequence is super important. And that's where grid LSTM steps in. It's like an LSTM, but, supercharged, ready to handle these long-range dependencies that really matter. We're looking at this research paper that really gets down into the details, the nuts and bolts of this new architecture. Get this, it's not just theory. Grid LSTM has shown some really impressive results in a bunch of different things, from like crunching numbers to translating languages, even recognizing handwritten digits. This thing's got some serious range.
Yeah.
But before we get too far ahead of ourselves, let's start with the basics. LSTMs, those long, short-term memory networks, are all about handling sequential data, like text or time series, right? They're designed to remember information over time, kind of like how our brains store and retrieve memories.
Yeah, and what's so fascinating about LSTMs is that they really revolutionized how we deal with that sequential data. They're incredibly powerful for things like, speech recognition and natural language processing, where the order of information is really, really important. But they do have their limitations, especially when you're dealing with very long sequences.
Oh, yeah, right? Like if you try to remember a conversation from weeks ago,
Mm-hmm.
some details might stick, but others are gone.
Exactly. And in neural networks, that's called the vanishing gradient problem. It's almost like playing a game of telephone, The message changes as it passes from one person to the next. In a neural network, that message is the gradient. It helps the network learn. And as that gradient travels back through the layers, it can get smaller and smaller. And that makes it hard for the network to learn from those earlier parts of the sequence. That's where Grid LSTM comes in with its, innovative approach.
Okay, so grid LSTM comes in to save the day. The paper mentions something about extending LSTM cells into this multidimensional grid. How does that actually help with the whole vanishing gradient problem?
Okay, picture a standard LSTM, like a single-story building, right? The rooms are the LSTM cells. They're all connected in a row. Information goes from one room to the next, but it's all on that one floor. Now, Grid LSTM is like a multi-story building. It has connections not only across the rooms on the same floor, the time steps, but also between rooms on different floors, which are the layers. This allows for a much richer flow of information. It stops things from getting lost as easily.
So instead of just moving forward in time, information can jump between different levels, like taking the elevator instead of walking down a long hallway, right? That's pretty brilliant. It gives the network this like more holistic view of the whole sequence, so it can capture those really important long-range dependencies. But does this fancy architecture actually mean better performance? I mean, sometimes things look good on paper, but don't actually work well in practice.
Oh, you're totally right to be skeptical. But the research here is pretty convincing. They tested Grid LSTM on a bunch of, algorithmic tasks, like adding up long sequences of numbers and memorizing symbol sequences. And they compared it to traditional stacked LSTMs.
So like a neural network Olympics, seeing who can crunch numbers fastest and remember the most. What were the results?
Grid LSTM consistently outperformed the competition. For example, in the addition task, a grid LSTM with 18 layers aced the test with way fewer training examples than a stacked LSTM needed. And here's where it gets even more interesting. They found that grid LSTM works really well with something called weight tying, which basically helps make the model smaller, reducing the number of parameters it has to learn. So you get awesome performance with a leaner, more efficient model.
That's a win-win in my book. Less computational overhead A&D, better performance, I'll take it. So Grid LSTM isn't just some theoretical show-off. It can actually walk the walk. But let's move beyond these algorithmic tests. Can Grid LSTM handle the real world? Because, that's where it really counts.
Right, that's the big question. And this paper actually dives into some pretty exciting real-world applications. One that really stood out to me was character-level language modeling.
Character-level language modeling? You mean predicting the next character in a text, like those autocomplete features we see everywhere?
Exactly. But imagine taking that to the next level, where the model needs to consider a much longer context to make those predictions. That's where Grid LSTM shines. They trained it on a massive Wikipedia dataset, a whopping 100 million characters. And it achieved state-of-the-art performance. It beat out other neural networks at predicting the next character.
Wow, so Grid LSTM can hold its own in the language arena. It seems like this architecture is really pushing the boundaries. Now, speaking of language, how does Grid LSTM handle something as complex as translation? I mean, it's not just about swapping words. You need to capture all those nuances and the meaning. I'm curious to see how they tackle this.
That's where things get really innovative. Instead of the traditional encoder-decoder approach, the researchers came up with this fascinating concept called the Reencoder model.
Reencoder. That sounds interesting. How is it different from the usual way of doing translation?
Well, imagine like you're translating a sentence from English to French. In the typical encoder-decoder framework, you'd encode the entire English sentence first and then decode it into French. The reencoder, though, works more like a two-dimensional map. One dimension handles the English sentence, the other handles the French.
Wait, so you re-encoded the source sentence on the fly. That's a completely new way to think about translation.
Exactly. And what's brilliant is that it acts like an implicit attention mechanism. As it's building the French sentence, the reencoder keeps going back to the English sentence, paying attention to different parts as needed. It's almost like a chef constantly checking the recipe while adding ingredients, making sure everything comes together right.
That's a fantastic analogy. So it's not just blindly translating word for word, it's actually understanding the context and how the words relate to each other in both languages.
Exactly. And one of the key insights from this paper is that the reencoder is particularly good at capturing those tricky translation invariances related to position and scale. You know, how word order can be completely different in different languages.
So you're telling me this reencoder model can actually outperform those phrase-based systems, the ones that have been the gold standard for so long. How is that even possible?
It's pretty remarkable, isn't it? They tested the reencoder on a Chinese English translation task, and it actually did better than a state-of-the-art phrase-based system.
Wow, that's a huge accomplishment. Beating a state-of-the-art system in machine translation is not easy. It seems like this Grid LSTM-based reencoder is a real game changer. Okay, so to recap, Grid LSTM is this new neural network architecture. It takes traditional LSTMs and adds this multidimensional grid structure. It tackles that vanishing gradient problem head-on, letting it learn those complex, long-range relationships in data. And it's not just theoretical. This thing can handle real-world tasks like character-level language modeling and machine translation, and it's getting some impressive results. It seems like Grid LSTM is living up to the hype and then some. But before we get too carried away, let's take a break and then dive into another amazing application of Grid LSTM. Image recognition. You heard that right. This versatile architecture can even tackle the visual world.
Welcome back to our deep dive on Grid LSTM. As we were saying before, this architecture isn't just limited to sequences and language. It can also be applied to image recognition, and the results are pretty remarkable.
Image recognition. That's a whole other ballgame. We're talking about analyzing pixels and edges and shapes, figuring out what's in a picture. How does Grid LSTM even approach that? It seems so different from sequences.
Yeah, that's what's so exciting about this research. They're really pushing the limits of what neural networks can do. In this case, they used a 3D Grid LSTM for images, treating the pixels as a 2D grid and adding the network's depth as the third dimension. It's like combining the power of CNNs, those convolutional neural networks, with the memory capabilities of LSTMs, and all across 3 dimensions.
Okay, I'm trying to picture this. So instead of feeding the whole image to the network at once, they break it down into smaller chunks, right? And each chunk becomes an input for the 3D Grid LSTM.
Exactly. They divided the image into smaller patches, and each patch is the initial input for a 3D Grid LSTM block. Now, here's the really clever part. The computation flows through the network in all 3 dimensions. The image's 2 spatial dimensions and the network's depth.
So it's like each layer of the Grid LSTM is scanning the image patch by patch. But unlike a regular CNN, which has a limited view, the Grid LSTM can, theoretically see the entire image context within each layer.
Yeah.
Because of those recurrent connections, it's like giving the network a panoramic view instead of just a snapshot.
You got it. And because we have those LSTM cells along the depth dimension, features from the current patch can be passed on to the next layer, either raw or processed by the layer itself, all based on information from neighboring patches. This creates a really dynamic and flexible way to analyze the image, allowing the network to learn a hierarchy of visual representations.
So it's not just looking at individual pixels by themselves, it's actually understanding the relationships between different parts of the image. Almost like a human would. It's like a CNN, but with a memory, right?
Yeah, that's a great way to put it. It remembers what it's seen in other areas of the image and uses that information to make better decisions about the current patch. And the paper shows that this approach is surprisingly effective. They tested this 3D Grid LSTM on the MNIST handwritten digit recognition task, a classic benchmark in computer vision.
Right. That's the one with all the handwritten numbers, 0 to 9.
Yeah.
Researchers use it to train and test image recognition algorithms. It's like the hello world of computer vision.
Exactly. And the results are pretty impressive. This 3D Grid LSTM got near state-of-the-art performance on MNIST, even without any pooling layers, which are usually standard in CNNs to reduce the data dimensionality.
So it's competing with the best CNNs out there, even though it's a completely different kind of architecture. That's amazing. It seems like Grid LSTM is pushing the boundaries in both natural language processing and computer vision. This architecture is a real overachiever. But let's not just skip over the details. Can you walk me through how they actually trained this 3D Grid LSTM on MNIST? What were some of the key tricks and insights from the paper?
Well, they followed some standard practices, like normalizing the pixel values of the images and using data augmentation to create more training examples. By slightly shifting the images horizontally and vertically, this helps the network generalize better, so it can recognize digits no matter where they are in the image.
So they're making sure the network doesn't get confused by small variations in the data. Clever.
Right, and they experimented with different patch sizes, using both 2x2 and 3x3 patches. They found that the smaller patch size worked a bit better, which makes sense because smaller patches let the network see finer details of the digits.
It's like zooming in on those handwritten numbers so the network can really analyze the individual strokes and curves.
Exactly. They use several layers of Grid LSTM, stacking them on top of each other to create a more hierarchical representation of the image. They also added a layer of ReLU units after the Grid LSTM layers to introduce some nonlinearity into the network, which helps it learn more complex patterns.
ReLU units, those are the ones that act like a switch, right? Deciding whether information should pass through or not. It's like adding another layer of complexity to the network's decision-making.
Exactly. They use the atom optimization algorithm, which is a popular choice for training neural networks, and they set the learning rate to 0.001. They trained the network for several epochs, meaning they went through the whole training dataset multiple times until the performance on a separate validation set stopped improving.
So they're really optimizing the training process, and the results show it. Near state-of-the-art performance on MNIST is a big deal, especially for an architecture that wasn't specifically designed for image recognition. I'm blown away by how versatile Grid LSTM is. It handles sequences, language, images. Is there anything this architecture can't do?
It really shows the power of thinking differently and challenging those conventional neural network designs. And the paper even hints at using Grid LSTM for even more complex data types, like music or video.
Music and video. Now that's exciting. Imagine being able to analyze, like, the dynamics of a symphony or the visual flow of a movie scene. Using this multidimensional processing power, it opens up so many possibilities. Okay, I'm officially a Grid LSTM fan. It's clear that this architecture could revolutionize how we process and understand all kinds of data. But before we get too carried away, let's take a step back and consider some potential challenges and limitations. Is there anything in the paper that suggests any drawbacks or areas for future research?
So welcome back to our deep dive on Grid LSTM. You know, as we were talking about before, this architecture really isn't just a one-trick pony. It's not limited to just sequences and language. It can also be applied to image recognition, and the results are pretty amazing.
Image recognition, that's a whole different ballgame. We're talking about analyzing pixels and edges and shapes,
Right.
trying to figure out what's in a picture. How does Grid LSTM even begin to approach that? It seems so different from sequences.
Well, that's what I love about this research, you know. They're really pushing those boundaries, what neural networks can do. So in this case, they applied a 3D grid LSTM to images. They treat the pixels as a 2D grid, right? And then they add the network's depths as the third dimension. It's like taking the power of CNNs, those convolutional neural networks, and fusing it with the memory of LSPMs and doing it across all three dimensions.
Okay, so I'm trying to wrap my head around this. So instead of like feeding the entire image to the network all at once, they break it down into smaller pieces, right? And each of those pieces becomes an input for the 3D grid LSTM.
Exactly. They divided the image into smaller patches, and each patch is the initial input for a 3D grid LSTM block. Now, here's the really cool part. The computation flows through the network in all three dimensions. The image is two spatial dimensions, and then the network's depth.
So it's like each layer of the grid LSTM is scanning the image, like patch by patch. But unlike a regular CNN, which has a pretty limited view, the Grid LSTM can theoretically see the entire context of the image within each layer.
Yeah.
Because of those recurrent connections, it's like giving the network a panoramic view instead of just a snapshot.
You got it. And because we have those LSTM cells along the depth dimension, features from the current patch can be passed on to the next layer, either in the raw form or processed by the layer itself. And it's all based on information from neighboring patches. This creates a really dynamic and flexible way to analyze the image. It allows the network to learn a hierarchy of visual representations.
So it's not just looking at individual pixels in isolation, it's actually understanding how different parts of the image relate to each other, almost like a human would. It's like a CNN, but with memory.
That's a great way to put it. It remembers what it's seen in other parts of the image and uses that information to make more informed decisions about the current patch. And the paper actually provides some evidence that this approach is surprisingly effective. They tested this 3D grid LSTM on the MNIST handwritten digit recognition task. It's a classic benchmark in computer vision.
MSHE.
Right.
Right. That's the one with all the handwritten numbers, 0 to 9. Researchers use it to train and test all sorts of image recognition algorithms. It's like the hello world of computer vision.
Exactly. And the results are pretty impressive. This 3D grid LSTM achieved near state-of-the-art performance on MNIST, even without using any pooling layers, which are typically used in CNNs to, reduce the dimensionality of the data.
So it's competing with the best CNNs out there, even though it's a totally different type of architecture. That's incredible. It seems like Grid LSTM is really pushing the boundaries in both natural language processing and computer vision. This architecture is like a real overachiever. But let's not just gloss over the details here. Can you walk me through how they actually trained this 3D Grid LSTM on MDIST? What were some of the key tricks and insights from the paper?
Well, they followed some pretty standard practices, like normalizing the pixel values of the images, and they used data augmentation to create more training examples by, slightly shifting the images horizontally and vertically. This helps the network generalize better, so it can recognize the digits regardless of their exact position in the image.
So that they're making sure the network doesn't get tripped up by small variations in the data.
Yeah.
Clever.
And they also experimented with different patch sizes, using both 2x2 and 3x3 patches. They found that the smaller patch size worked slightly better, which makes sense because smaller patches allow the network to capture those finer details of the digits.
It's like zooming in on those handwritten numbers, letting the network really scrutinize those individual strokes and curves.
Exactly. They used several layers of grid LSTM, stacking them on top of each other, to create a more hierarchical representation of the image. And they also added a layer of ReLU units after the grid LSTM layers to introduce some nonlinearity into the network, which helps it learn more complex patterns.
ReLU units, those are the ones that act like a switch, right?
Yeah.
Deciding whether or not information should be passed on is like adding another layer of complexity to how the network makes decisions.
Precisely. They used the atom optimization algorithm, which is a popular choice for training neural networks, and they set the learning rate to 0.001. They trained the network for several epochs, meaning they went through the entire training data set multiple times until the performance on a separate validation set stopped improving.
So they're really pulling out all the stops to optimize that training process, and the results speak for themselves. Near state-of-the-art performance on MNIST is a huge accomplishment, especially for an architecture that wasn't specifically designed for image recognition in the first place.
Yeah.
I'm blown away by how versatile Grid LSTM is turning out to be. It can handle sequences, language, images.
Yeah.
Is there anything this architecture can't do?
It really is a testament to the power of thinking outside the box, challenging those conventional neural network designs. And the paper even suggests that Grid LSTM could be applied to even more complex data types, like music or video.
Music and video. Now that's getting me really excited. Imagine being able to analyze, like, the temporal dynamics of a symphony or the visual flow of a movie scene. Using this kind of multidimensional processing power, it's like opening up a whole new world of possibilities. Okay, I'm officially a Grid LSTM fan. It's clear that this architecture has the potential to revolutionize how we process and understand all kinds of data. But before we get too carried away with all the excitement here, let's step back for a second and consider some potential challenges and limitations. Is there anything in the paper that suggests any drawbacks or areas for future research?
You're right. It's always important to be aware of the potential pitfalls, even with a promising new technology like this. One potential challenge is computational complexity. As we discussed earlier, the Reencoder model that they use for translation, its complexity can grow pretty quickly as the length of the sentences increases. This could become a bottleneck when you're trying to apply Grid LSTM to very long sequences or really massive data sets.
So scaling up could be an issue, especially for real-time applications where speed is essential.
Exactly. Another challenge is interpretability. Neural networks, especially complex ones like Grid LSTM, are often seen as these black boxes because it's hard to understand exactly why they make the decisions they do.
Right, it's like they have this mysterious inner workings that we humans just can't quite grasp. That could be a problem in applications where transparency and explainability are crucial, like medical diagnosis or financial modeling, for example.
Exactly. While there has been some progress in developing techniques to interpret neural network decisions, it's still a very active area of research. And it's something that needs to be addressed if we want to fully trust and rely on Grid LSTM in those kinds of critical applications.
So while Grid LSTM is a powerful tool with huge potential, we need to be mindful of those limitations and approach it with a healthy dose of caution. But even with those challenges, I'm still incredibly optimistic about the future of Grid LSTM. It's a truly innovative architecture that's already proven itself across a variety of domains. And with ongoing research and development, who knows what other groundbreaking applications we'll see emerge in the years to come. This has been a truly fascinating deep dive into the world of Grid LSTM. We've explored its inner workings, its strengths, its limitations, and its potential to reshape how we interact with data and intelligence. But our exploration doesn't end here. We encourage you to continue learning, questioning, and exploring the ever-evolving landscape of artificial intelligence. Who knows what amazing discoveries await us just around the corner. Until next time, keep those deep dives going and never stop exploring the fascinating world around us.